people. But those who don't see the connection, I will not explain. And then I will say few things toward that. So let's recall what is a classical linear code. So a classical linear code is nothing more than a vector subspace of z2 to the n of dimension k. So the finite field of order 2, just 0 and 1 of dimension k. The rate, this is called the code. Of course, by this we say is nothing. The important thing is the qualities of the code. There are two main parameters. One is the rate of the code, which is k over n, and one is the distance of the code, which is the minimum weight of alpha, where alpha is some non-zero vector in the code, where the weight of alpha is the so-called Hamming weight, namely the number of i's such that the coordinate ai is different than 0. Basically, we all understand what is a code. We want to send a message of size k. We map it by a linear map to a space of dimension n, and now if we want the code to be efficient, we want that the rate will be large, and if we want it to correct mistakes, then we want the distance between 2 points in the image to be large. If the distance is d, you can correct d over 2 mistakes. Delta is the normalized distance, and the standard notation is that C is NKD code. Now, what is a quantum error correcting code for us? Now, I want to stress right away, because now I don't want to explain and to talk about the more general. I'm specializing right away to the so-called CSS quantum error correcting codes. This is Calderblanc, Schur, and Siden, or something like that. What? Zin. Okay, and this is a somewhat special case. On the other hand, many of the code discussed in the literature are really falling into this family. And now I'm using not so standard notation, not in the standard notation, but it's been slightly more convenient for us. So a quantum code for us will be a pair of two subspaces of z2 to the n, which are orthogonal to each other. Orthogonal when we take two vectors and we multiply the inner product, of course, with the mod 2 binary operation. And so what does it mean? They are orthogonal to each other. It means that W1 is inside W2 perp, in the perpendicular to W2, and W2 is in W1 perp. And here is the definition of a dimension of a code. This is a definition of a quotient space. This is K equal W1 perp, the dimension of W1 perp over W2, or the dimension of the quotient W2 perp over W1, and they are equal. This is a trivial linear algebra exercise, and both are equal to n minus dimension W1, dimension W2. What is the distance of such a code? The distance is the minimum weight, but Hamming weight, but now let's be careful, over all vectors alpha, so that alpha is in W1 perp, but not in W2, or in W2 perp, but not in W1. Namely, we allow to have vector with short support, with a small weight, inside W1 and W2, but not in the orthogonal of them unless they are in W1 or W2. This is the distance of a code, and the standard terminology in this case that C is NKD code with double brackets, where the rate is again K over N, and delta is delta over N. Now, the following definition applies to both cases, classical code and quantum code. We say that the code is good if there exists some epsilon greater than 0, such that delta and R are greater than epsilon. So, at this point, we are a real mathematician, you know, our n is going to infinity, and we are interested in when we say a code, we really mean a family of codes, and we want good codes, namely the delta and r, the distance, the normalized distance, and the rate are both bounded away from 0. We need another important definition. This is important also in the classical code theory. The code is called LDPC, low density parity check, if C perp, the perpendicular to C, is spanned by vectors of bounded weight. Let's explain for a second why this is such an important notion. You see, if you want the receiver, just think classically, the receiver is getting a message and you want to check whether this is a legitimate message. So the question is whether this is in the space. The easiest way is to check whether it is orthogonal to the complement. If you know, if you are getting a set of vectors in the orthogonal perp which spans the perp and of bounded weight, then you have very short equation to check. You check only bounded number of values from the message, and you see that that there are no mistakes. For quantum code, C is LDPC if both W1 and W2 are spanned by vector of bounded weight. You might be surprised I ask you for W2. In some sense, the important objects are Wi perp. And what we want is that the dual, that the perp of Wi perp will be spanned by short vector. And that's the right notion for quantum error correcting codes. But here comes a first difference, at least in our knowledge, between classical codes and quantum code. Good. Now the question, can we achieve all the conditions together? Can we achieve codes that will be good and LDPC at the same time? So good LDPC classical code exists. This is a famous work of Gallagher. Well, actually, it became famous much later. Only much later people understood how his work is important, because I think at the time, you know, when people use codes where the length was 8 or 100 or 256, then bounded, then n was not really going to infinity. Let's put it this way in practice. But nowadays, when they are working with error correcting codes of size 200,000, 200,000 is a better approximation to infinity. And then this notion of the code are kind of is important. And then there was a real breakthrough in '96 by the work of Sipser and Spielman, who used Ramanujan graphs to construct explicit constructions of a good LDPC classical work. Let me explain why no, sorry, okay. So, okay, so that's the classical. I don't have time to explain too much here. But let me say now about quantum. Good quantum error correcting code exists. This is work of several people. I didn't put on the desk. I forgot. Shor, I think, involved in that, and several others.
Shor called
Lubotzky. Okay, but it's still an open problem. Are there good LDPC quantum code? This is open also randomly. It's not clear. Why? What's the difference? Why this is not the random is not even a difficult result of Gallagher. It's kind of by nowadays standard. Here it's difficult in the sense that you have to use Ramanujan graph. But if you have Ramanujan graph, then you really need Ramanujan or close to Ramanujan, not just expander. Then the work of Sipser and Spielman is not so difficult. But here it's not even known randomly. Why? Because the work of Gallagher basically says the following. It's sort of imitating the original work of Shannon. How Shannon proved that there are good code. He said take random equations and take the set of solution to some random equation, so this will be a good code. And Gallagher said, take random short equations. If you take a random short equation, you can think of it as a vector in a W perp, and then you define W by that, and then some of kind of a standard computation show you that you get good code. But what's the problem with the quantum? If we take W1, we need W1 and W2, and we take W1 to be random, and then, then exactly by the computation of Gallagher, in the complement, there are no short vectors. So we cannot really take random W2. We cannot take random W1 and W2 at the same time because they won't be orthogonal to each other. So this is such an elementary problem, you know. I mean, it took me a few minutes to describe it, but this is an undergraduate, first year undergraduate problem which really fascinated me by its simplicity, and that's the problem I want to discuss. I mean, I cannot solve it. I'll want to tell you a few things about it. And what's nice, at least from my point of view, that it really suggests some interesting problems in kind of a pure mathematics.
Alex,
Yeah.
just to stop you, and probably because I understand very little. What's the role of the two W's in the quantum code?
The W1 and the W2 are, I think, what you call the Pauli. You probably are more familiar with the language of the stabilizer code. So these are kind of the Pauli operations in how many mistakes you find. How many they check, do you have an error or not?
Why do you need
The LX and the LZ, the X parameter and the Z parameter. Barbara will
two? More kinds of mistakes.
You have two types of error, X and Z, or part of X and Z. That's what
Okay.
we're saying.
Now I want to show you that's a little bit more frightening words, but it's still, if you will see, it's a first year undergraduate linear algebra, even though the title is fancy, homological quantum error correcting code. So let me do it in the simplest possible way, and we'll define quantum homological quantum error correcting code. Oh, okay, why we are going to this situation? Usually we think that, okay, in experience is to get some good codes, and the LDPC is the new object which is difficult. In the homological code that I present you, at least in the way I present it, we will get the LDPC for free. These are codes which are LDPC almost for free, and then the question, are they good or not, or what are the qualities of them, and they relate to some interesting geometric or combinatorial problem. That's what I want to show, and then that's what I will discuss. Okay, so let X be a finite simplicial complex of dimension D. For example, you can take a triangulation of a manifold. So simplicial complex, you can think of it either as something concrete, you know, vertices, edges, triangles, pyramids combined together, or in an abstract way as a collection of subsets of X0, that's the notation, the set of vertices of the simplicial complex. And the property is that if F is in the collection of subset and G is a subset of F, then G is also in the collection. Namely, if we have a triangle is in, then all the edges are in. If we don't have like triangles in and one of the edges is not in. Okay, that's just a formal thing. Here is notation Xi is the set of all I-dimensional faces. I-dimensional face means a subset with I plus 1 points. So one vertex is a 0-dimensional face, an edge with 2 points is a 1-dimensional face, etc. So X1 is edges, X2 is triangles, etc. Now, I'm giving you, I mean, I admit for those who never saw it, it might be fast, but as you can see, it's completely elementary. I give you a 5 minutes crash course in homology and cohomology. I know that these are fancy words, homology and cohomology are one of the most successful theories of the 20th century mathematics. So let me do it. But if you do it over Z2, you suffer less. So it's actually, the intuition is to start over R, but over R you have to put orientation, and then over Z2 you'll see that it's much easier, and it's elementary linear algebra. So let Ci be the terminology is I chain. What means I chain? You take the set of all I cells and you take the vector space over Z2 whose basis is this set of I chain. So the dimension, for example, is the set of I chain. You take C upper I to be all the functions from Xi to Z2, the I cochain. Well, you can think of this as two different sets, right? This is the vector space of the spanned by the chain, and this is the function of them. But between you and me, this is the same thing, right? Like this, because what does it mean if you take a function on the set of cell, it give its values either 0 or 1. So it means either you take it or you don't take it. So it will be convenient to confuse ourselves. It will be really convenient here, and to think of them as the same thing, and sometimes to think about it as Ci, and sometimes to think about it like that. Now we have the boundary operation, which is a map from the space of I cells to I minus 1 cells. What is the, now in order to define a linear operation, it suffices to define it on a basis. The bases are the cells. So I take sigma I of a cell is the sum of all G in F, which are of dimension I minus 1. Very simple. Think about the dimension 2 to 1. The image of a triangle is the formal sum of its edges, or of its three edges. I'm stressing. If you take a pyramid to triangles, then the sigma of a pyramid is the formal sum of the 4 triangles around the pyramid. This is called the boundary map. And delta I is the co-boundary map, and this is if you start with a cell of dimension I, you sum up over all the cells of dimension I plus 1 containing that F. So if you start with an edge, then you go to dimension 2 and you take the formal sum of all the triangles lying on that edge. These are the co-boundary, the boundary and co-boundary operation. There are two very easy, well-known facts, and it's just a 2 lines calculation that I don't have time to expand here, which say that if you apply one of these after the other, they are 0. Sigma I after sigma I plus 1, delta I plus 1 after delta I. Sigma is going down, delta going up. But anyway, if you apply twice, you get the 0 map. What does it mean? It means that the image of sigma I plus 1, the boundaries of I plus 1 is something in the Ci. So this is the boundaries. I will denote it Bi. The image of this is inside the kernel of the next map, right? If this map after this map is 0, it means that the image of this is inside the kernel of this. And this is called the I boundaries, and this is called the I cycles. Now, if you again, in a proper course, I'll have to stop here and to show you example about graph. And then you see that one cycle are exactly cycles in the graph, closed cycles in the graph.
Sums.
What?
Sum of closed cycles.
Sum of closed cycles. And okay, and Bi now, okay, that's from this equation. From this equation we get that the I co-boundaries namely the image of delta I minus 1, is inside the I cocycle. This is just now, we call it cocycle because it's kind of formally the same. And the famous homology and cohomology is nothing more than the quotient space. This kernel, namely the Zi divided by Bi, is the H lower I, which called the cohomology of the ith cohomology of the homology of the complex, and H upper I is Z upper I divided by Bi is the cohomology. Okay. Now, but there is another easy corollary of fact 1 which should work out. Another, it's a 4 lines exercise which shows you that Bi perp is exactly Zi, and B upper I perp is exactly Z lower I, and you remember this one contains this one and this one contains this one, so we have a quantum code. We have automatically every simplicial complex for every I gives you a quantum error correcting code of type CSS. So the pair boundaries Bi and co-boundaries, okay, this pair is a CSS quantum code, and this we will call homological code. Okay, but as this is just like in the classical theory, every subspace is a code. So if I give you 2, but not every subspace is a good code or not even close to be good. But also here, the fact that I'm getting 2 subspaces does not give the orthogonal to each other. That's a good start, but it's only a start, not even good start. The question is, what are the parameters? But the parameters have some interesting meaning. And the length of C, first of all, is the size. They are subspace of the space of cochain equal to the space of chain. So the length of the code is the number of I cells. So this has a combinatorial or geometric meaning. The dimension is the dimension of Bi pair divided by Bi, or the dimension of Zi divided by Bi, which is the dimension of the cohomology. It's well known that over field, the homology and cohomology are of equal dimension, but we know that, right? In a quantum code, this is the same thing, right? I mean, so either you compute it like that or like that. So here is an interesting phenomena. The dimension of the code is something that, we are the mathematicians are very interested, is the dimension of the homology of the complex. The distance of the code gives some new challenge to mathematicians, but challenge which is semi-familiar. Let me explain. The distance of the code is the minimum, by definition, right? Is the minimum of the weight of alpha, such that alpha is in you remember W1 pair, but not in W2. In our term, now, if we apply it here, so this is in Zi, but not in Bi. Namely, alpha represent a non-trivial element of the cohomology group. Alpha is represent a non-trivial. Or alpha represent a non-trivial element of the homology group. And we want that non-trivial representative of homology and cohomology will be long. Let's think back about graph. What does it mean for graph? We said before the cycles are. So in graph, this would say that the length of the minimal cycle in the graph is long, what is called by combinatorial people the girth of the graph, which something which even came up in this conference, something which was heavily studied in graph theory. Moreover, the representatives of homology and cohomology classes the minimal length of them is a but it's an object in Riemannian geometry, goes under the name of systolic geometry. like many things in geometry, is led by Gromov. There are several deep proof of Gromov, but almost all works are in the analog situation when you replace Z2 by the integer or by the real numbers, like characteristic 0 game, and not over Z2. In some sense, here is an example where a problem coming from quantum codes is kind of an inspiring for mathematician to really start. I mean, it's of kind of independent mathematical interest, but of course, it's give more motivation if you see that there is some kind of an application to study this type of problem. This problem I don't have time to really elaborate, but it started with you have a manifold and you want to ask what is the minimal closed cycle, which is not, you cannot homotopic it to trivial, or to get it shorter, and then you can ask about higher dimensional cycles in homology. For mathematicians, these are natural questions to ask.
But it's not exactly length.
So well, it will be some kind of an area if you go, and that's actually going to play an important role here. So this is really the Hamming weight of a minimal non-trivial or homology or cohomology class. Yeah, and this is the subject. Okay. Now let me say something important for us. That if now, as we said before, we are really interested in an infinite family, not just one code. In the infinite family, you have a family of simplicial complexes going getting the number of vertices getting larger and larger. Now, if they are all coming as we like to think about, like all of them are I don't know, surfaces, which something that one can give this interpretation to some of the codes studied, surface codes, etc. Then the local geometry of them is the same, and then what you get that automatically, for example, if all the x's are finite sheeted cover of one finite complex, x1 now is not the one skeleton. I have one object and I take the finite sheeted cover of it. For example, then I'm getting families here of quantum codes which are automatically LDPC. This property, which looks a bit difficult to achieve if you think abstractly, when you come from the geometry point of view or the combinatorial point of view, it's very natural and you get it almost for free. The question is, can you, in this situation, get also that the dimension, that the rate, the dimension will grow linearly, the rate will be bounded away from 0, which means in this language that the dimension of the homology or the cohomology grows linearly with the size of the simplex. Okay, finite sheeted cover means, yeah, oh yeah, so okay, think about it, let's go back to graph. If you take a graph, if you think about any k regular, any graph which is 3 regular, you can kind of pull it down to the, I don't need really finite sheeted cover. What I really need is to say that they have a similar local structure. What? Yeah, finite, right, the links are finite. Okay, or even simplest. I stressed before, I said that the boundary of a triangle is always of size 3, right? So there is a bound 3, and all the boundaries are generated. The size of the co-boundaries is the degrees in how many triangles contain an edge. And if this is bounded, then we get LDPC for free, and we have plenty of examples of that. So this property is sort of for free. And now, and if you go and check, and again, I don't have time for that, then many of the known quantum algorithmic codes, for example, Kitaev Tori codes, etc., are really homological code. I mean, maybe in the first definition they were not presented in this fancy language, but basically you can easily put them into this framework. But up to now, the optimistic point of view. But then, a few years ago, a very pessimistic point of view was presented, and this is a conjecture of Zemmour. He checked all the known examples in the literatures, and also he has some intuition coming from classical code. And he said, okay, homological code are wonderful. Let's be honest. I mean, I want to be modest and honest. You know, I know that you don't really care about n going to infinity. Let's face it. But if you will succeed with quantum computation, then one day you will be interested in n going to infinity. Just like in the Gallagher was ignored in the 60s because nobody in the classical code was interested in n going to infinity. Only mathematicians treated this case. And nowadays, LDPC is maybe the most central issue in coding theory. So hopefully in 50 years, this also be this LDPC. Anyway, but Zemmour's conjecture was that if C is a homological code, then R times delta square is always less than n to the minus 2 plus little o1. So which means that when n going to infinity, little o of 1 means that this goes to 0. Or if we translate it back to the language of, the reason, by the way, delta is giving a kind of double importance is that delta appears on both sides of the game. You know, in W1 perp mod W2, etc. Anyway, this was his conjecture because of checking various examples and some intuition. And all examples indeed satisfy that. And he conjectured that k times d square, which means, if that's just a translation, is at most n plus little o1, namely when n going to infinity, this goes to 0. This is very disappointing, because what we want that k will go like n, and d will go like n. So we want that k d square will be something like n cubed. And then it tells you that it's really not more than n. That's a conjecture, at least. So his conjecture is that, okay, homological code are very, very nice and for that, but they will never give you. A student of mine, Etan Fataya, in fact, proved last year Zemmour conjecture for if you start with triangulations of manifold of dimension 2. Okay, so it gave some evidence, more evidence to the conjecture of Zemmour okay, the good news of my talk is that Zemmour conjecture is not true. And the rest of my talk, which will need a little bit of more sophisticated mathematics, I have to admit, will present some new families of codes or going to some more fancy type of manifold, which will give counterexample to Zemmour conjecture. But I want to be honest with you and say that we are going to beat Zemmour conjecture by very, 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 very little. Some of you may want to go to sleep now. For those I will say now that in some sense our work is of no importance. Because we are presenting new homological codes, they beat Zemmour conjecture. I'll try to explain what was, it's more important that they give insight and understanding what was wrong in Zemmour intuition, and they put back the homological code into the race of getting good LDPC code. They say, they give some optimism that there is a chance to get a LDPC good code. There are, Zemmour himself, some time ago with Lichik, found a LDPC code, which is not good, but are even better than us, but not homological. So, I mean, the codes I'm going to present you by themselves, I think, are not important. But I think they will explain some geometric intuition, and they suggest that maybe the geometry or combinatorics here can help you eventually to get good homological error correcting codes. So I guess most of the audience can now go to sleep. I guess most of them sleep anyway. But okay, so here I have another, what, 10 minutes or so? 7, okay. So I'll have to go very, very quickly. I really apologize, but now I have to talk kind of to the expert, just that you'll get a feeling. So up to now was, if we take the following quadratic form, fx1 up to x5 is x1 square, blah, 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 minus square 2 of x5 square, we'll take the group preserving this quadratic form over the reals, and gamma an arithmetic lattice of this Lie group G. An arithmetic lattice means the points over the ring of integers. I'm taking a specific one right away. Z plus z square root, which is the ring of integer in the quadratic extension q square root 2. So our group gamma will be those elements in GL5O which preserving this quadratic form. Now, this is, I may even skip all this and just say that this is a standard in the theory of arithmetic lattices, work of Borel, Arishan, Ramos, Otamagawa. Many of the big names of the 20th century spend their life on working on things like that. That you see, the group SO for 1 acts on the 4-dimensional hyperbolic space, and when you take now I defined before gamma using this ring of integer O. If you take an ideal in this ring of integer O, you can define a congruent subgroup gamma I, which is the kernel from gamma to GL5 O mod I. This is a finite ring, so this is a finite group. So this is a finite index subgroup. So H4 modulo gamma I is a 4-dimensional hyperbolic manifold, constant curvature -1. Now let's fix the triangulation of M1, namely gamma 1, the full group, and let Xi be the pre-image of this triangulation in Mi. Now, by definition, this gives us simplicial complexes, and this gives us, as I explained before, quantum error correcting codes, actually in several dimensions. But here is the main theorem. Here is the main theorem. There exists constant epsilon. Okay, so let me before I read the theorem, and because in some sense the most important point is to run away from dimension 1 and dimension n-1. In some sense, that is really our kind of new insight. Why Zemmour was wrong? Because he looked at the all example, and naturally all the example will build from surfaces which are dimension. Now the toric examples are not necessarily from small dimension, but they are bad because they don't have exponential growth for a different reason. But the toric are kind of clear cannot be good in the long run. You know, I know the toric are very important here, but when n will go to infinity, they are so poor because they really correct a bounded number of bits. You know, and that's kind of ridiculous when n going to infinity. But you know, that's the way everything starts. But so one really should go to kind of exponential growth. But among the exponential, if you work with low dimension, here is the big difference between 1 and 2. You have to look. You see, if you look at dimension I, then because of Poincaré duality and the duality between I and n-I, you really at the same time, you do homology and cohomology. I'm sorry that now I'm talking a little bit for the expert. You really look also at n-I. So you really have to make sure that you are neither in I equal to 1, not I equal to the dimension -1. Now, if you do with 2 and 3, you cannot run away from 1 and n-1. You have to go to 4. So 4 is the first case that you have I such that I and n minus I are not 1. So we have to go to dimension 4 and we have to work with homology and cohomology of dimension 2, which is actually even convenient because of the Poincare duality. They are dual to each other, so we have to prove a theorem only for homology and automatically true also for the cohomology. But the key step that you really are the point that you have to step, you can, if you really opt to solve the problem, this problem through geometric methods, dimension 4 is the minimum dimension to start, and you have to run away from dimension, from working with I equal 1 or I equal to the dimension minus 1. That's really the...
You have to work with manifolds.
No, you don't have to. You can take simplicial complexes. What?
Then you won't have Poincare duality.
No, but okay, right. Then you will not have to work. But if you then you don't have to worry about n minus 1. You're right. I'm trying to think about Ramanujan complexes. The problem is to try to get also a large homology. You see, without Poincare duality, it's very difficult to find situation that you have both homology and cohomology growing linearly. So, you know, you lose something on this side of that. Okay, but you're right. Anyway, here is the technical theorem. There exists some constant epsilon 1 and epsilon 2, which can be such that, you see, we look at exactly the same construction I made before, applied to this manifold, and then I say the dimension grows linearly with the volume of the manifold. That's exactly what we need. That's fantastic. It means that the rate of this code, the dimension of this code is linear in both sides. This is fantastic. The distance is not so good, but it's not terrible, but it's not so good. For every homological non-trivial Z2 2-cycle or 2 co-cycle, and it's enough to prove it for 2 cycle, and by Poincare duality you get this automatically, the area is at least the volume to the epsilon 2 power. If I could take this epsilon 2 and put it in front, then we'll be winning. Right? But unfortunately I cannot. Anyway, because in our case n is x, y, xi the dimension grows linearly with the volume. The real meaning of the theorem is that we are getting that k times d square is greater or equal n to the 1 plus epsilon double prime fixed epsilon. So we are beating Zemmour conjecture, but very, 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 very little. Just like passing the threshold of 1, but not by much. And we know to prove, I will save you a question, we know to prove that they are not much better than that. I mean, we are not sure what the exact, we can compute epsilon 2 and lower and upper bound for that. Anyway, the main new insight is that 2 systole is very different than 1 systole. And here I can add one more or less, just a moment. I will not even try to give the proof, so I'll just concentrate on this as my last remark on this remark. I will say, I will try to explain why 1 is poisoned. 1 is poisoned for a very simple reason. In this type of game, when like hyperbolic or exponential growth, if you look at this systolic geometry, which study minimal representative of non-trivial homology, so in dimension 1 it means minimal GERT, and this is logarithmic. There's always logarithmic. You know, there is not linear is not here, but you know, a lot of people working what's the best constant time logarithmic, but you cannot win it logarithmic, so that's the best you can achieve. When you go to higher dimensional systolic geometry and you want to ask what's the minimal size, the minimal representative of a non-trivial homology or cohomology class, then you have a chance to do much better. In particular, in this case, we manage by imitating some classical results from systole geometry over R to adapt the technique to systole geometry over Z2. and to get that it n to the epsilon. In principle, maybe one has a chance to get in other situation that it's even linear in n. There is no reason. With 1, it cannot happen. And n minus 1, or dimension minus 1, because upon current duality, it won't happen. So you have to go to a middle size, and then maybe you have a chance. So I will finish here with this optimistic point of view that maybe somebody will be able to do much better by picking up other manifolds. Thank you very much.
So, other questions, remarks?
I can do it.
Even linear with n would not give you good quantum codes, right?
No, that's a if
You get square root of
no. If it will be, if the systolic geometry, like the question is, what is the representative? What is the size of a minimal representative to the homology of cohomology? We were able to prove that the size of it is n to the epsilon, at least n to the epsilon. If we could make epsilon to 1, we win. Then we get good LDPC codes. Then it would be fantastic. We know to prove that in these cases, the epsilon is at most, I don't know, for some reason, 4/15 or something like that. I have to compute it again. Because of existence of some two-dimensional subsurfaces, which arithmetic subsurfaces appear. But it's not out of the question. Now we can construct other example that our method to give an upper bound do not exist, but still we don't know to prove that there is better. But no, I think there is a fair good chance that this may suggest somebody smarter will come up. I mean, basically, what we are saying, don't take the pessimistic point of view of Zemmour. This gives an optimistic point of view that there is a chance to get via homology and cohomology good quantum LDPC quantum code. That's the message of the talk.
I think what?
Yeah. Oh, Shlomo, yeah.
Does Chigger's inequality come into these?
What?
Does Chigger's inequality come into these?
The Chigger inequality, not directly, though. You know, this systolic geometry, in a sense, is some kind of a similar style of isoparametric inequality. You know, the systolic is kind of you can think of it in some sense as a Chigger inequality. Right? Yeah, in fact, you can even think of it as a higher dimensional version of Chigger inequality. I can, in one way of thinking, yes. Actually, yes.
So Kitaev four-dimensional code, which is based on the torus, has some additional pleasant physical property that under certain assumptions the system sort of self-correct itself in some physical terms. So maybe there is some hope that this similar result will be moved for your code with our code.
If you will explain me what it means, maybe I'll be able to answer, but I don't know enough to do this analogy.
I think that's interesting. Yeah.
What?
It depends on the geometry of these. Well, I don't know. We can take this.
What? No. Maybe you are a good translator between the two
well, I don't know,
communities.
the point is that if you have for a two-dimensional toric code, the logical operators are strings, huh? So it relates to the cohomology, and therefore you can make them. So if you say I want to make, it's dangerous for the environment to make such an error, and it can make it by having by creating an error that let's see, that is well, that probably says an energy. Okay, let me just forget about this.
Okay, we can talk.
I can tell you.
So my question is, do you have an estimate of how general are these homological codes within CSS? It's called CSS quantum codes. I mean, they're very special.
Probably.
It's clear that code cannot be represented.
I mean, if you just
represented somehow.
Yeah, but that's the same thing. You know, like you don't expect that it will be general. Like, you know, the Sipser-Spielmann code are fantastic, and they're very spatial. Usually, the extreme spatial cases give you the best results. So that's the fact that.
No,
It's not clear, I don't know.
But I mean, starting with a code, can you find?
Represented,
Yeah.
Yeah.
logic.
Yeah, probably quantum weights element codes would might be.
But I don't know.
Do you know of any meaning the intersection form might have for the quantum code?
Oh,
The manifold has some intersection form.
I'm afraid that I am not the guy
The
to.
intersection form, that's the common invariant of the manifold. My question was whether it is known to have any meaning for the quantum code. I'm not aware of any.
Interesting. I don't know. It's interesting if there is a meaning in the. Now you're saying, okay, up to now, as a mathematician, I'm inspired by the quantum type question. Now you want to go back and say, okay, there are some good things, maybe they can help, or that would be wonderful, and that's exactly what the center here is about. But
But it
I'm
doesn't
afraid
play a
no.
role in your proof.
Not really. No, I think not really.
Okay, so let's say Alex again.
מה?
לא מרגיש שיש היגיון סיסטולים גם בממד יותר גבוה. לא בממד אחד.